Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a lecture on functions for intermediate algebra and now college algebra. We've already completed parts A through E, so we've just finished our conversation about base graphs. If you do not know what a base graph is, if you don't know what the basic 8 graphs are, then I would recommend watching that prior to watching this video. In this video, we're going to focus on transformation of functions, in other words, moving and manipulating those base graphs that we just learned. And we'll play around with these for quite some time. I'll introduce a way to understand transformations of functions in a much easier format than I think what a textbook would deliver. The way I've always taught this is by making a table. And in this table, I'm going to talk about the graph of a basic function here. Just some random function that somebody's given me. So suppose that somebody gives you the graph of f of x. Just a function. It could be f of x equals x. It could be f of x equals x squared. It could be f of x equals the sine of x. Something. And just some type of function they give you. And then you do some manipulation to it. In other words, you might want to look at the graph of negative f of x, or 5 times f of x, or f of x plus 8, or f of negative x, or f of 3x, or f of x plus 4. All of those cases present us with interesting effects on the graph of f. So this is what I have. I have these separated into things that happen on the outside of the function. So notice in this first case here, the negative is on the outside of our function f. This a is also on the outside of our function f. And this plus k is also on the outside of the function f of x. And when I say the outside, I mean that those 3 things in red are not within the parentheses. They're not our inputs. On the other hand, the stuff that's happening on the inside is like this negative. This negative is on the inside of the parentheses, so it's part of our input. This a times x, that's part of our input. And x plus h, that's part of our input into the function. So I just want you to know why I call these the outside and the bottom group the inside group. Also, we'll notice something very special about everything that happens on the outside versus what happens when we manipulate the inside of a function, what happens to the graph. The way I'm going to justify these is through an example first. And each one of them will probably elicit its own example. Some will be easier to understand than others. But I'll try to restrict myself to a handful of examples. Our first example is this. How does the graph of g of x, which is a negative x squared, differ from the graph of f of x, which is a positive x squared? In other words, I know I'm given some function f of x that looks like the standard parabola. I'm just going to quickly kind of jot that down. And I want to know, if this is f, the graph of f, I want to know, how does g differ from that? And can I use the graph of f maybe to help me find the graph of g? Well, let's think about what that negative does. It essentially, well, actually, you can almost write it like this. G of x is equal to a negative, and then, isn't it just negative f of x? In other words, if f of x is equal to x squared, I'll replace this x squared here with f of x, so it's just a negative f of x. Well, that might not help you if this is your first foray into substituting in functions for other functions or whatever. So it might help to say something like, you know what is happening here? This is like a graph of y equals x squared. If I throw a negative in front of this x squared, that means that all the y values would change signs. In other words, all of these outputs that are at these heights here would all of a sudden be negative outputs. They'd be reflected, essentially. So we'd get a graph like this. Now you can always test this out by just making a table of values for x and f of x. In other words, I could, for f of x, I could plug in -2, -1, 0, 1, and 2. And you'll see that its outputs will be 4, 1, 0, 1, 4. And now make a corresponding table for g of x. Remember, g of x is just negative x squared, so I'm going to plug in negative 2 again, negative 1, 0, 1, and 2. If I plug in negative 2 in there, I get a negative 2 squared, which is positive 4 times a negative. And the same thing will be for all of these cases. You'll get this beautiful table of values here, which you notice that all the outputs in the G column are opposites of the outputs in the F column. In other words, they're just mirror images about the x-axis. So that's how it actually differs, is that you're essentially making mirror images about the x-axis. By the way, I'm using x squared here, but had our initial function looked like, let's say this, sort of like a cubic, then if I were to multiply that, let's say that's positive x cubed, if I were to multiply that by a negative, again, all the y values would swap positions. They become opposites. So you'd get something like this. That's a negative x cubed. Everything from here just rotated around and swap positions, or in other words, reflected about the x-axis. So the graph of the opposite, or the negative, of f of x looks just like the graph of f of x, except it's been reflected about the x-axis. And I will write down that that's a vertical. I'll say vertically, because that's a vertical reflection, up-down type of reflection. And you should always try to understand why this is true. So maybe with each of these I'll just put the question mark why. And the reason why is because all the y values end up changing signs. What was up is now down, and vice versa. What was down is now up. So that's our justification in a way as to why that's true. Now let's go ahead and take a look at what happens when we multiply the outside of a function by some number. To do this, or demonstrate this idea, I'm going to go ahead and take one of our base functions, f of x equals the square root of x, and I'm going to manipulate it. I'm just going to multiply it by 5. So I want to graph the square root of x, and also I'm going to graph 5 times the square root of x just to see how they differ. Now to do this, I already put down a set of axes here. I made a table for the square root of x, so when 0 is input into that, we get 0 for the output. Plug in 1, you get 1 for the output. Plug in 4, square root of 4 is 2, and so on and so forth. And now I'm going to make a table for 5 times the square root of x. When you plug in 0, well, square root of 0 is 0. 0 times 5 is still 0. You plug in 1, square root of 1 is 1, times 5 is 5. Plug in 4, square root of 4 is 2, times 5 is 10. And then plug in 9, square root of 9 is 3, times 5 is 15. You see that each of the outputs is multiplied by 15. It's 15, or multiplied by 5, sorry. So it's 5 times larger. And that's the way you could think about this, is that this basically takes all the outputs and makes them 5 times larger. Now, I'll write that down in a moment, but I want to graph this first so you can see this. So 0, 0 is right here. And then 1, 1 is right there. And what do we say? 4, 2. So that's 1, 2, 3, 4, 2 is right there. And then 9, 5, 6, 7, 8, 9, 3. So we get something like this. This will be our square root function. I'll just connect those up with a nice smooth curve. So you can see how that sort of looks if I could actually draw a curve smoothly. And it is, remember, a function that continually grows. It just grows kind of slowly. Now the black curve, on the other hand, goes through 0, 0, and then 1, 5. 1, 2, 3, 4, 5. All of a sudden it's way up there. And then 4, 10. So it's 1, 2, 3, 4, 2, 4, 6, 8, 10. Then 9 comma 15, I just didn't want to bore you with that rambling on my part. So I go ahead and connect these points with a nice smooth curve. As smooth as I can make it, drawing freehand, not looking at my hand. And you can see that this is a much taller graph. In fact, if you were to describe this graph in relationship to the red graph there, a lot of people will say it's very tall, it's been stretched, and actually the word that you want to use is that it's been stretched. It's been stretched by a factor of 5, and in fact that's what I'll go ahead and write here. Stretched by a factor of 5. So everything's 5 times as tall. So it turns out that if you want to graph a number times your function, it'll look like your original function. It's just everything's been stretched away from the x-axis by a factor of 5. Notice, though, something very important to notice. Anything on the x-axis stays in place. So notice that the original function y equals root x went through 0, 0, and so does this function. 5 times the square root of x also goes through 0, 0. So you're stretching, you can imagine like Play-Doh, like you have a line of Play-Doh along, I don't know if this makes sense to you, but you have some type of line of Play-Doh here, whatever it is. You could smear it away from the x-axis in both directions, but it cannot actually, if it was originally attached to the x-axis, it will never leave the x-axis. So you're just smoothing this away a little bit. I don't know. I don't know if that makes sense to you. Now let's see what happens if instead we were to multiply by a fraction, a proper fraction that's less than 1 in magnitude. In other words, it's just a number between 0 and 1 here. Well, first thing I'm going to do is I'm going to have to put down a set of axes. And then I'm going to want to create a table of values for just to get a perfect graph for my f of x equals x cubed. And I know that I can't really plug in huge numbers. I'll put -2, -1, 0, 1, and 2. I already know what the base graph looks like. And generally the idea of using a base graph is just to get a basic idea of what the graphs look like. The whole point of graphing using this method that I'm teaching you right now is not to be perfect, but to have a great understanding and idea of what the graph looks like in general without even having to graph it. But for right now, because I'm kind of showing you what each of the effects of these things is, I have to be pretty exact here. So -2 being cubed is going to be a -8. And we have a -1, a 0, a 1, and an 8. And now I'll go ahead and take a look at plugging in 1/2 here. I'll do that in black. So I have 1/2 of x cubed, which basically means if I use the same inputs, all my outputs will just be half of what they were before. So this will be a -4, this will be a -1/2, this will be 0. Notice that the point that goes through the x-axis still remains at a height of 0. It's 1/2, and this will be a 4. And I'm going to plot both tables. This is what's very difficult about graphing by hand. It's really difficult to see, but remember the red curve represents our original base function. That's our base graph for y equals x cubed, or in other words, our cubic base graph. And the black curve is 1/2 of that. And if you think about it, 1/2 of that means that all these heights, the stuff that was originally at this height right here, is now, for the black curve, half that height. And the stuff that was originally at this height right here is now at half that height, somewhere down there. Same thing, the stuff that was along the red curve right here is now at half the height for the black curve, and so on and so forth. Everything gets half of its original height. So this right here is saying that we compress all y values by a factor of 1/2. So everything's 1/2 closer. Now, I've heard arguments, by the way, for the language of this, and I agree with both. I've seen textbooks written that say that that these y values have been compressed by a factor of 1/2. which I don't know if I 100% agree with, but if that's what your textbook says, that's what you go with. And I've seen it written where it's compressed by a factor of 2, and I agree with that as well. Because when you talk about compressing something, generally we say we're going to compress it by a factor of 2. It means it's half its original height. So it's kind of implied in the statement. But compress all outputs by a factor of a half is perfectly fine here. So what's the lesson in all this? The lesson is that the graph of a number times f of x times our original base function looks just like the graph of the original base function, except it's been either stretched or compressed vertically by a factor of a. It's been stretched if the number that you're multiplying by is greater than 1. So 3, let's say. That means that all the outputs are 3 times their original height. It's been compressed if the number you're multiplying your function by is less than 1 but bigger than 0. So in other words, like 1/10. Everything's 1/10 its original height. And if you want a good kind of idea, again, you should always ask yourself why, because that's what children ask themselves, and that's when you've learned the most in your life, is when you ask why a ton of times. So if you want to know why this is true, it's because all the y values are being multiplied by a. That's what that a out front is doing. It's saying a times the y values. So all the y values are being multiplied by a. So if there was a y value of 10 before and a is 3, that y value is now 10 times 3, or 30. So now let's take a look at f of x plus k. Again, I'll just create a completely different example using one of our base graphs here. So in this case, let's play with the absolute value function. We're going to go ahead and graph the base graph of the absolute value, and then finally graph g of x, which equals the absolute value of x plus 4. Let's write down some values for the absolute value function, even though we know it's going to look like a v. Let's write a -2, -1, 0, 1, and 2, and we know quickly that these are just going to be these values here. For the absolute value of x plus 4, again, I'm going to go ahead and plug in the same inputs. This time, absolute value of -2 is 2, plus 4 is 6. Absolute value of -1 is 1, plus 4 is 5. And in fact, I could just look over at these values and just keep adding 4 to them. Because that's all this is plus 4 is doing, is it's adding 4 to all the original y values. So right from the table, I can easily see that what this 4 is doing is it's adding 4 to all the outputs. But what does it do visually? Well, let's plot these values and find out. As you can see, I plotted in red all the values for f of x equals the absolute value of x, and in black I've plotted all the values for g of x, which equals absolute value of x plus 4. And I can see that essentially what happened here is that all the outputs got lifted up by a factor of 4, or by 4 points. So you see we've moved that point up 4, this point up 4 units, this point up 4 units, that point up 4 units. All the y values have been shifted up 4 units. And the same thing could be said if there was a subtraction there. If it was a -3, it would take the original graph and move things down 3 units. Therefore, we can kind of easily say that the graph of f of x plus k looks just like the graph of f of x, except it's been shifted up or down k units. Up if k is positive, down if k is negative, and that shift, I know I said up and down and same vertically is kind of repeating myself, but the fact is I need to say it because I want you to see that essentially everything that we've done to the outside of the function here has affected things up and down or vertically. And in fact, I want to put a little plus above the word up and a minus around above the word down, because we generally associate the first word up with plus and the second word down with minus. So that's how I'm going to kind of associate these two. In fact, maybe I'll clean up that plus sign because it's not really the best in the world. And now we're going to turn our attention to the stuff happening on the inside of the function to see if there's some correlations there. I forgot to mention the whole y behind that last one. It's because all y values are being added to by k. So in other words, all the y values get to change. They get to grow by amount of k. All right, let's play with the cube root function now. In this one, we're going to go ahead and graph the cube root of x and then the cube root of negative x. So notice that there's a negative on the inside of that. So now we're dealing with the inside stuff. We're going to see what happens here. Often you don't find an intermediate algebra book that has stuff with a negative on the inside of the function going on, but I still want to talk about it just because I think an education should be complete and not incomplete. And I forgot to write this in here, so I'm going to write cubed root of a negative x here, and y equals the cubed root of x there. Alright, I'm just going to plug in values that I know I can easily take the cube root of, like 8, and let's see, we'll take the cube root of 1, 0, oops, I should say negative 8, negative 1, and then positive 1 and positive 8. And I'll use the same values over on the other one here, negative 8, negative 1, 0, 1, and 8. Now, the cube root of negative 8 is negative 2, the cube root of negative 1 is a negative 1, 0, 1, and 8. On the other hand, we're not looking at the cube root of a negative 8 here. We're actually looking at the cube root of a negative 8. In other words, the cube root of positive 8 is actually what we're being asked to find here, because the negative inside will cancel with that negative when I plug in the negative 8 for x. So this will turn into a positive 2. Same argument can show that this will turn into positive 1, this will turn into a 0, this will turn into a negative 1, and this will turn into, whoops, not a negative 8. Negative 2, and in fact I should probably change this as well so that people don't yell at me. Okay, there we go. Alright, so let's plot these points. The graph in red represents the cubed root of x, so that's our original function, and the graph in black represents the cubed root of a negative x. Now, this is where it gets kind of tricky, and this is probably why intermediate algebra textbooks don't address this issue. But it often is the case that whether the negative's on the inside or the outside, it makes no difference. Well, it's not always the case, though, but it happens quite often, actually. In this case, you'll see that some people will visualize this and say that it's been rotated about the x-axis. Well, technically, you probably could say it has been, actually. But I'm going to draw your attention the other direction and say, could you visualize, or ask maybe, could you visualize that this has actually been rotated, so that red curve has been rotated around the y-axis? It actually has. So all of these points along this red curve here get reflected about the y-axis and are graphed over here. And same thing about the ones on the red curve on this side, they get reflected and they're on the black curve on the other side. So it does get reflected about the y-axis. Not the best example in the world. After I started doing it, I thought, shoot, this is not going to be the best example. But it turns out that when you have a negative on the inside of your function, it is a reflection about the y-axis. Although in this case, like I said, it would make no difference if you saw this as a reflection about the y or about the x. It actually is the same. And in fact, possibly a better function to have shown this with would be the square root functions. And in this case, I'll just save time and show you on a graphing calculator. If you want to look at the square root function, second square root of x, and let me zoom standard so that I have the standard square root curve. There it is right there. And now if I want to look at the square root of a negative x instead, and hit graph, there's the square root of negative x. Notice it is a reflection about the y-axis. So that's a little more convincing, actually. Therefore, the graph of f of negative x looks just like the graph of f of x, except it's been reflected about the y-axis, which is a horizontal reflection, or in other words, a left-right reflection. It reflects about left, right. And again, the y of this is a little more difficult to grasp. The best way I can describe it is that the role of x that we would originally plug in, say x equals 3, is now being portrayed as the opposite of what it originally was. So in other words, when I think I'm plugging in x equals 3, what the function's interpreting is that I'm plugging in negative 3. So it's looking at what negative 3 would have been. In that mindset, you can kind of see, oh, whatever I plug in, the function is thinking I'm plugging in the opposite value. So it's going to paint the picture for the opposite side of that y-axis. And that's exactly what's happening here. Now let's move on to f of some number times x and see what this does. Now honestly, this idea of a transformation, or this type of transformation, f of some number times x, is very difficult to do with the functions that we know. So what I have to do is actually get a function that you don't know. This is the sine curve. So in red we have the sine curve. And in blue, which you can't see, is the exact same curve. It's just sitting underneath. Let me show you that this is true by adding 1 to the outside or adding a little bit to the outside. Now watch what happens when I add a little bit to the outside of the function. I just added a 0.1, a 0.2. Remember, when you add to the outside of the function, something happens up and down. And you see if I'm adding 0.3, it's shifting that red curve up 0.3 units. And I can keep going, it keeps shifting up and up and up. Okay, so that's not that big of a deal. That's not what I'm actually going for. What I'm going to demonstrate to you is what happens when I multiply the inside of f of x by a number that's not just 1. Now let's see. What if it was 1.2 or 1.3 or 1.4? What's happening to this graph? And this is super important to see with this kind of curve. This is called a sine curve. Very, very important for you to see it with this curve because most students don't have an exposure to this kind of functional curve until way later on, and that's the first time they're able to actually understand, oh, that's what multiplying the inside of the function by a number means. So if I'm going to increase this, let's just say f of 2 times x versus f of x. F of x is in the red curve, f of 2 times x is in the blue curve, and what did that do as I increased that number? It looks like it's compressing it horizontally, right? Like an accordion. Well, what would happen? So that's if the number's large, bigger than 1. You see that the curve is compressed. But look, what would happen if I wanted a number less than 1, like 9/10 or maybe 0.8? This seems to be, if you think of this as a spring, it seems to be uncoiling or stretching that spring out. And that's exactly what happens. Now the big question is, what's happening here to make this do this? Well, let's go back to where we have just f of x and then we'll increase it. So let's say I'm looking at f of 1.5x. Essentially when I plug in x equals 2, what the function thinks is that I'm plugging in x equals 3 because it's plugging in 1.5 times 2. Or I'm plugging in 2, but it's thinking I'm plugging in 1.5 times 2. So what it's doing is when I want to plot 2, instead of plotting out a value this high, it's going to the value of 3 and saying, oh, he wants it to be that high, about 0, about a height of 0. It's very difficult initially to understand it, but if you spend some time pondering it, it might help out. In fact, if you look at this, let's look at what happens when we plug in x equals 4. For the normal function, when you plug in x equals 4, the output looks to be about a -1. I mean, it's not really, but let's just say it's about a -1. Now let's change our function here to be f of 2x. Now remember, with the red function, when you plug in 4, the output is roughly a -1. Now with my blue function, when I plug in 4, the blue function thinks I want to know what f of 8 is. If I really want to know what f of 4 was, I'd have to plug in x equals 2. So if you plug in 2, 2 times 2 would give me 4. So look, when you plug in 2, you're down here at a height of almost negative 1. So again, you have to spend some time to kind of wrap your mind around that. It's something more of a playful thing for your brain than it is a necessary item, but still kind of neat. Same thing with going 1/2 x. Whenever you plug in a value of x like 4, if you plug in x equals 4, well, f of 4 is at a height of, again, like I said, round negative 1. But when I plug in 4 to the other function, it thinks I want to know what f of 2 is, which would be f of 2 is roughly a positive 1. So when I plug in 4 for x into the blue function, it thinks, oh, what, f of 2? Yeah, you're roughly about a height of 1, which is exactly what that f of 0.5 times 4 is. So anyway, that's a good way to kind of play with this. This is under function transformations under the Wolfram demonstrations project. So check this out, and you can also play with like linear functions, quadratic functions, cubic functions, all this stuff. It's really kind of fun. So to sum that up, f of a times x is basically the same as f of x, except it's been stretched if a is between 0 and 1, or compressed if a is bigger than 1, by a factor of a horizontally. So notice this is opposite of what the outside stuff did. Remember when on the outside, right here, when a was like 3, that meant everything was 3 times as big. That makes sense. But here, when a is 3, it means that everything is squished by a factor of 3. It's kind of counterintuitive. And that's pretty traditional for the stuff that happens on the inside. The stuff that happens on the inside usually is opposite of what you would think. And if you thought that was tough, just read this y on this one. The role of x is now being played by a times x. And for example, if a is greater than 1, like 3, let's say, then things are happening 3 times faster. In other words, instead of when you plug in x equals 1, the function doesn't think you're plugging in 1, it thinks you're plugging in 3. So if you want to plug in a group of numbers between 0 and 1, and you plug them in like 0 and then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.91, the function thinks you're plugging in 0, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.7, and 3. In other words, it thinks you're plugging in faster, larger values. So that's why it gets compressed if a is greater than 1. Again, good luck on getting that wrapped around your brain. It might take a couple courses to finally get that one. The other one, the last one here, f of x plus h, that's more of the basic one. That one is covered in intermediate algebra class. The first two in this group, these two right here, usually are not covered in an intermediate algebra class, but this last one definitely is. So let's take an example. Let's go ahead and graph the standard squaring function here, the prototype for the squaring functions, and then g of x equals x plus 2 and quantity being squared. Making a table of values. For x squared, I'll plug in -2, -1, 0, 1, and 2. So my outputs will be 4, 1, 0, 1, and 4. I'll use the same inputs for this other function, and something odd just might happen. And I think I had warned you that tables are really horrible ways of graphing functions, and this is exactly why right here. When I plug in -2, I'll get -2 plus 2, which is 0. And then squaring that gives me 0. And you think, wait, okay, so what just happened? Well, let's see what happens when you plug in -1. Plus 2 is 1, squaring is 1. Plug in 0, plus 2 is 2, squaring is 4. Plug in 1, plus 2 is 3, squaring is 9. And plug in 2, plus 2 is squaring is 4, squaring that is 16. So what happened? Well, let me plot these values first. Plotting the tables as I have made them shows me, well, the standard parabola in red, but our kind of manipulated parabola here, the x plus 2 quantity squared, shows only half of it. The reason why is because often, like I said, building tables is just not going to work out well. So we need to choose more values. We only got half the parabola. Let's try x equals a -3 and x equals a -4, just to see what happens. If you plug in x equals a -3, -3 plus 2 is a -1, but squaring that gives me a +1. -4 plus 2 is a -2, squaring that will give me a +4. And if I plot those points, let's see, -3, 1, -4, 4, right? Around there. And I connect those points, you'll see I get the second half of the parabola. So I guess I do have the proper graph. It's just that I didn't build my table big enough. That's the problem with building tables. Like I said, the third time, right? Very bad that I say it so many times. But let's notice something here. These two graphs almost look exactly the same. Pretty good job. Let me pat myself on my back. The only difference is that the black parabola has been shifted to the left 2 units. Notice it went to the left 2 units, not to the right, but to the left. So you would think that +2 on the inside would actually move it to the right in the positive direction, but it moves opposite that direction. And that's what I had mentioned a moment ago, is that normally when you're doing stuff on the inside of a function, it goes opposite of what you would think. You would think this would move to the right. It actually moves to the left 2 units. So let's go ahead and write that down. So the graph of f of x plus h looks just like the graph of f of x, except it's been shifted left if h is greater than 0, or right if h is negative, h units horizontally. This kind of shows you that everything on the inside does things left or right. Let me write that down. Shifts left or right. And in fact, I'm going to do the whole plus minus business as well. The first word I always say is left, the second word is right. It's mainly because I'm left-handed, but also because it's a proper way to say it. Just kidding. So anyway, but most people do say left, right, not right, left. So if you say left first, then right second, the first word gets a positive. That means that if it's a +5, then we're shifting left. If it's a -10, we're shifting right. Okay? Now let's try these newfound skills on a very complex problem. Let's go ahead and graph h of x equals a -2 times the square root of x minus 5 plus 1. When you do this, you always read from left to right. So let me write that down. You read these from left to right. The reason why is because if you don't, you risk the chance of messing things up, essentially. Let's go ahead and try this out. What I highly recommend doing is you start with a small base graph. Here's my base graph. This is the y equals the square root of x. There's the parent or the prototype for this function. The prototype function is the square root of x. When you peel away the negative, the 2, the -5, and the +1, you just have a square root of x. And now, from this point forward, I'm going to go ahead and graph in here each of these transformations. So the next one is I'm going to apply the negative. That negative on the outside will flip this graph. So it'll look like something like this. And remember, it's always flipped about the x-axis. So this is y equals a negative square root of x. And then I apply the next transformation, the 2. You just have to make things twice as tall as they were before. Oops, that might be a little bit much. But notice that I'm not really being super exact here. I do have a significant difference between the last graph and this graph, which is y equals a -2 square root of x. It's just I'm not being super exact because that's not the point of graphing using transformations. When you graph using transformations, you want a basic idea of what the graph looks like. Now we apply that -5 on the inside of the function. So let me go ahead and draw my set of axes. Each step I usually like to see a set of axes here. Remember, when you have a minus when you're working on the inside is opposite of what you think. You would think that would shift you to the left 5 units, but it actually shifts you to the right 1, 2, 3, 4, 5 units. Otherwise, the graph looks exactly like the previous graph. Very steep and kind of broad there. That's the graph so far of y equals a negative 2 square root of x minus 5. Now, of course, we have one more step, the plus 1. This will be our very final graph. Get that nice in there. We were already shifted over 1, 2, 3, 4, 5. And now, here's where I pretty much took advantage of the anchor point in when I started shifting left or right. Once you have to do left, right, up, and down, I usually just grab the anchor point and move that over 5 units. And then now the anchor point has been moved over 5 units. That plus 1 means it's going to be moved up 1 unit. So remember I made kind of a big deal talking about the anchor point when I was talking about base graphs. It's because it really does help you graph your function or shifts and translations of your functions in the long run, because you can just graph that or grab that anchor point and use that for your shifts and transformations. And this is the final graph. H of x is equal to a negative 2 times the square root of x minus 5 plus 1. If I read it out loud, I would say, this is how I would say it, how I would kind of tell somebody what I've done. I've flipped it vertically, stretched it by a factor of 2 vertically, shifted it to the right 5 units, and then shifted it up 1 unit. That's exactly what you see when you read through those graphs. Now let's play with one that I've avoided filling with this entire time. The reason why is because I wanted to get the basics of shifts and translations down first, and then we go into the more advanced stuff. The inverse functions are the ones that are a little bit more, well, challenging if you're not careful. What you need to do when given an inverse function like 1 over x or 1 over x squared, and you see the base function for this is 1 over k squared. Our variable is k, so I have to use that. When you're given that, you definitely want to write it as some number times that. In other words, there's 3 over 4, so I'm going to write this as 3/4 times 1 over k plus 1 being squared minus 6. The only reason why I do that is because it makes it extremely obvious that, oh, I'm multiplying the outside of it by 3/4. Otherwise, some people think they're multiplying the outside of it by 4 or by 3, but not 3/4. So just a word to the wise. Now, when graphing this, you also have to be very careful because you have to constantly be aware of the vertical and horizontal asymptotes. So let me go ahead and start a graph of this. Now remember, 1 over k squared sort of looks like this. Just going to quickly draw it just like that. And I'll even put in the vertical and horizontal asymptotes. Now, because they are on the axes right now, it's not that big of a deal, but in the long run, once we shift things left and right, I'm going to be grabbing the asymptotes to do that. So that's a graph of y equals 1 over k squared. Now I'm going to start applying the transformations here, like this right here, the 3/4 on the outside, reading from left to right. 3/4 on the outside. Well, that number is less than 1. That means that I'm going to compress this graph vertically. Now, to be honest with you, it won't look like much of a compression. It'll actually look kind of like the same graph. However, if you have a very strict instructor, then it's probably best to show that it is at least closer to the x-axis here. So, oops, I am drawing the wrong way there. Freehanding this, so. Well, that's essentially it. You see that it doesn't really look that much different. If you have an instructor that requires you to plot a million points when doing this, then you would want to plot some points. But the fact is that, as I've mentioned before, the idea of using shifts and transformations is not for exactness, actually. It's for a basic idea of what the graph looks like in the long run. So this, what we have right now, is just our nice pretty graph of y is equal to 3/4 times 1 over k squared. Or if you really want to glue those two things together, 3 over 4k squared. Now the next one I have to put in here is, reading from left to right, that plus 1. So I want to put in the plus 1 now. So let's go ahead and try to figure out what that plus 1 does. Let's see, it's on the inside of the function, so that means that it's going to shift things left and right. The plus 1, I know you want to think it shifts to the right because that's the positive direction, but remember, everything that happens on the inside of the function goes the opposite direction of what you would think, so this is going to shift to the left 1 unit. So I'm going to basically grab this picture that I just created and shift everything to the left 1 unit. Now here's how I recommend that you do that. Grab the vertical asymptote and shift it to the left 1 unit. We didn't shift things up and down, so the horizontal asymptote doesn't move at all. Otherwise, copy your red curve. So my red curve looked like something like this. Again, I'm not being super exact because I personally am not that kind of instructor that needs exactness on this. It's one of my favorite topics, but it's also one of the more useless topics if you're forced to plot a ton of points. All right, so that is the graph of, let me change pen colors here, just to keep consistent. Y equals 3 over 4 times k plus 1 being squared. Now finally, I have the minus 6. So what we're going to do is apply the minus 6. Is the last thing that we have to do here. So I'll go ahead and plot a coordinate system. And I will manipulate my vertical asymptotes and horizontal asymptotes. Since we're not shifting left and right anymore, I'll just redraw my vertical asymptote here that's been shifted over to the left by 1. My horizontal asymptote has been shifted down 6 units. Well, that's actually going to be kind of off the screen in a way. 1, 2, 3, 4, 5, and 6. So my new horizontal asymptote is right here. Notice my x and y axes haven't moved. It's my asymptotes that have moved. But that asymptote, both those asymptotes give me a guideline of how to draw. So my x and y axes, I'll go ahead and label those in this last step anyway. This is the x-axis, this is the y-axis. Those don't change position, but I now know, otherwise my curve is going to want to hug these asymptotes here. And this is a graph of y equals 3 over 4 times the quantity k plus 1 being squared minus 6. Now for anybody who says that that is not the graph of that, grab a graphing calculator and check it. I know that there are some people that are sticklers for, oh, you have to be super exact when you do all this. So let's see how incorrect I am. The numerator is 3 divided by the denominator. Whenever you have a bunch of stuff going on in the denominator, start a parenthesis. 4 times the quantity. I don't have a k, I have an x plus 1. N quantity squared. So that ends the denominator there. And then minus 6. And I'll zoom standard here. And let's see, I have that. Now you might say, well, where are the vertical asymptotes? Normally, graphing calculators don't graph vertical and horizontal asymptotes. I could show you where the horizontal asymptote is. It's at y equals negative 6. So I can at least show you that one. Whoops. Let me go to here. I didn't mean to put the negative 6 there. And you notice my editing skills, I actually don't edit this out. It's awesome, right? Okay, so here goes the horizontal asymptote, right there, and it totally matches ours. And the vertical asymptote is just going to be a line that's in between those two. That's exactly my graph. So in their faces who tell me to graph things like this with perfection, you don't have to. So again, just pay attention. Anything that happens to the outside of the function either flips it up and down, stretches and compresses it up and down, or moves it up and down. Anything that happens on the inside of the function either flips it left-right, stretches or compresses it horizontally left-right, or shifts it left-right. The first two that I have arrows pointed at, and I shall highlight really quickly, these two right here, normally do not occur inside an intermediate algebra course. You might be lucky and be the one that gets a teacher who likes those. When you are presented with a problem, read it from left to right, like I said in this example with my McDonald's colors right here. Okay, so you read it from left to right, and you perform those transformations from left to right. What you should practice on doing is reading out loud what's happening to the original base function. You should read something like, well, go to the next problem here. Read something like this and say, oh, okay, what's happening is it's being compressed by a factor of 3/4. It's been shifted to the left 1 unit and shifted down 6 units. Okay. Once you can say that and even write it out, then doing each of these graphs step by step is going to be a cinch. Also, one last thing, when you're working with inverse functions like 1 over x or 1 over x squared, be sure to always draw in your horizontal and vertical asymptotes. They are your guidelines. They're like shadow axes, basically. There's these fake axes that you get to kind of move around and grab and play with. Finally, take a chance in life and actually go someplace else other than a lecture. Go to Wolfram's demonstrations project. There's tons of free demonstrations on there, and you can just search on here for, in their little search box, that you can search for transformations, and this is just one of them that came up. And you can select all different kinds of functions to take a look at. If you want to take a look at the square root function, there it is. And if you look at the format, we have a, which is going to be our number that we're going to multiply the square root by. So let's say we multiply it by a number larger than 1. See what happens. We're multiplying by 4.2. That means all the y values are 4.2 times higher. Or if you want to multiply it by a number like negative 4.2, everything's negative 4.2 times, right? The negative flips it, and then it stretches it. Okay. You could also do things like the inside of this function. If you have x plus 4.2, I keep laying out 4.2 for some reason, it shifts it to the right, 4.2, or I'm sorry, to the left, 4.2 points. If it's x minus 4, then you've shifted to the right 4 points. Finally, this is the up and down movements. So, okay, beautiful. That's all you need to know. I mean, it really is. You can play with this stuff all day long. There's a ton of them on this one. But, yeah, good times.